Welcome to the Green Parking Council webinar, Energy Efficient Ventilation Systems. This presentation is part of our continuing series of informational webinars on sustainable technologies and programs in parking facilities. I am Trevor Mead, Green Parking Council Program Manager. If you encounter any technical problems during the presentation, please email me at trevor@greenparkingcouncil.org or send a chat message in the box on the left-hand side of your screen. Please enter any questions into that chat box as well. We'll have 15 minutes at the end of the webinar to go through the questions we received during the presentation. The webinar will run no longer than 1 hour. New efficient ventilation technologies create a tremendous opportunity for parking garages to lower operating costs and environmental impact. Garage ventilation systems are one of parking structures' largest consumers of electricity. Today's presenters will highlight innovative technologies that drastically reduce this energy consumption while complying with evolving efficiency and safety standards at the local and state levels. We will learn about the different types of ventilation standards and codes, available technologies, and how they relate to Green Parking Council's Green Garage Certification Program. In addition, the presentation will conclude with a case study highlighting a garage that has transitioned to energy-efficient ventilation. Our first presenter will be Don Monahan. Mr. Monahan is a registered professional engineer and vice president with Walker Parking Consultants. He has 36 years' experience in parking facility design with specialized expertise regarding lighting, safety, and security of multi-level parking structures. Don is a member of the Parking Facility Lighting Subcommittee of the Illuminating Engineering Society and was a contributing author of the IES publication, Lighting for Parking Facilities. He is also past chairman of the Parking Consultants Council, past member of the Board of Directors of the National Parking Association, and a consultant member of the International Parking Institute. He is co-author of Parking Structures, Planning, Design, Construction, Maintenance, and Repair, and a certified parking facility manager by MPA. In October 1996, Don received the Bernard Dutch Memorial Award for Outstanding and Dedicated Service from the MPA. Don?
Thank you, Trevor. As parking consultants, the building code requires us to comply with mechanical ventilation of enclosed parking garages, which requires knowledge of how to best implement those systems. Older building codes required that the exhaust fans run continuously regardless of the level of vehicle emissions, which obviously uses excess energy. Changes implemented in the 2003 International Mechanical Code allowed automatic detection of vehicle emissions to activate fans if excessive levels of harmful vehicle emissions were detected. This approach was much more energy efficient. However, the code went backwards in 2006, requiring that the fans operate when the parking garage was occupied. That approach requires that the fans operate nearly continuously, as there is always either pedestrians or vehicles circulating in the garage, with fans often operating when harmful vehicle emissions were not even present. I've been lobbying the International Code Council for many years to adopt more energy efficient and realistic requirements for ventilation in parking garages. We vehemently objected to this new approach based on occupancy rather than demand-based control, and we lobbied the International Code Council to go back to detection of harmful vehicle emissions as the safer and more energy efficient approach. In the meantime, studies by ASHRAE and others indicated that the ventilation capacity could be decreased from 1.5 cubic feet per minute to 0.75 cubic feet per minute per square foot of floor area, and that was adopted by the International Mechanical Code in 2009. This was a major step in further reducing fan sizes and energy consumption. Using demand-based ventilation control in parking structure then is now significantly more energy efficient. However, this webinar will outline a new approach that further reduces energy consumption tied more closely to the actual level of vehicle emissions as opposed to just on-off control, with the new approach further reducing energy consumption.
Thanks, Don.
Now I'll turn it over to Mike Adelman.
Mike Adelman is the General Manager of Intech Controls. Intech has been a leading supplier of measurement and control devices for the commercial heating, ventilation, and control industry for nearly 25 years, and has been specializing in air quality applications since inception. Mike has over 34 years of experience in the measurement and control industry and began at Intech in 2010. He is a member of the Certification and Sustainable Technologies Committees of the Green Parking Council. Mike holds a degree in Operations Research from the University of California at San Diego and is a senior member of the International Society of Automation. Mike? Mike, I believe your line's muted. We can't hear you. Please hold for 1 second, folks. We've got a technical issue.
Okay, is that working now?
Yes, we can hear you now, Mike. Thanks.
Very good. I'm sorry. So good morning. I'm Mike Adelman, as Trevor introduced. So adding a little more information to what Don just gave us on the overview. Because there is safety elements involved in the ventilation of the garage, it's closely governed by various codes and measures. So I wanted to begin with an overview of how the codes has evolved and what the current state of best practices is. As Don mentioned, ASHRAE, the American Society of Heating, Refrigeration, and Air Conditioning Engineers, basically is the textbook on ventilation controls in all applications. Standard 62.1 is what touches the subject today, ventilation for indoor air quality. From the ASHRAE standards are derived model codes. The International Code Council is the widely accepted body for defining the model codes, and they write the International Mechanical Code, the IMC. Derived from that, then, are local building, mechanical, and energy efficiency codes that are owned by what's referred to as the AHJ, the authority having jurisdiction. It might be a city, it might be a state, but in any given location of the garage, there is a defined authority having jurisdiction. That's the evolution of the codes. So as Don mentioned, every 3 years the International Mechanical Code is updated, and beginning in 2003 was the first opportunity to utilize carbon monoxide detection to control the fans in the garage. So this is not 2015 technology. It is well-proven, established technology. What has changed is the details and the specifics of how to balance the energy efficiency with the safety component. In 2006, again, the student body right, the code was expanded to also, in addition to carbon monoxide, it allowed motion detection. Now, motion, as Don said, was vehemently opposed because of really two issues that were quite contradictory. One, a stationary vehicle emitting exhaust would not trigger the motion sensors, and secondly, humans and other motion through the garage would trigger the violation, trigger the ventilation, even though there was no event in terms of rising levels of carbon monoxide. So since 2006, again, with a lot of people advocating for the change, that needed to be done. In 2009, again, the design airflow was reduced so that the fan sizes could be reduced. 2012, because of the increased presence of diesel vehicles, which exhaust nitrogen dioxide as the toxic component of their exhaust, the 2012 update of the International Mechanical Code Section 404 brought into play carbon monoxide and nitrogen dioxide. And now the 2015 code, which was just hit the street June of last year, became effective June 14, very simply states that if fans are operated intermittently, it must be via CO and NO2 detectors. Now the if, of course, is an operative word. An owner-operator still has the option of running their fans continuously, which again would certainly provide a quite safe environment, but at an extreme inefficient cost. So that's the mechanical code itself. Layered on top of that are building efficiency standards. Where I am out here in California, it's referred to as the Title 24 Building Efficiency Standard, which touches on all aspects of the operation of a building, the occupied space, lighting, and ventilation for humans, and effective in the 2013 standard, which was again hit the street and became effective in 2014. For this first time, the California Title 24 code does now address enclosed parking garages. The specifics of how that code defines the ventilation system and its operation was driven by a task force that did research into the actual operation of garages, the effectiveness of systems that were already deployed, and again, weighed all of that information together to define the thou shalls from a go-forward basis. And California has been utilizing this Title 24 standard for many years, but many jurisdictions are adopting building efficiency codes that, again, add to the, if you will, minimum functionality that the ASHRAE and the mechanical code stipulate. This is layering on top of it best practices from the standpoint of building efficiency. So specifically now, the California code, and very similarly adopted in Oregon, Washington, and others as they adopt it, is requirement for continuous CO monitoring, carbon monoxide monitoring. So instead of even giving the option of running flat out, it is now required. It requires variable flow rate fans. Frank will be getting into the various types of ventilation controls between on-off and variable. The California Efficiency Code now mandates variable flow fans. It increased the density of the sensors. So the core sensing technology, the physics, the chemistry of detecting the carbon monoxide is well known. However, different vendors, as they deployed the technology into their devices, different manufacturers would stipulate different density rates. Well, in California, in order to kind of herd the cats, they have now embraced a 5,000 square foot coverage area for the sensor, basically superseding whatever a manufacturer's recommendation on that might be. So that is now a standardized deployment density. There's very specific algorithms, techniques for detecting a faulty sensor and what to do when one is detected. Because again, back to that task force, it found that although these systems have been deployed quite widely, many, if not most of them, are not functioning to their design capability. An analogy that I commonly use in this respect are tires on an automobile. If you want them to continue to perform safely and efficiently and with a maximum life, you've got to watch your air pressure, rotate, balance, etc. So there is periodic maintenance on those tires to make sure that you're again, maintaining safety and efficiency. Similar with the carbon monoxide sensors, the way they interact with the gas in the air, they do require periodic maintenance, not only in terms of the hardware itself, but again, humans can sometimes intervene, an operator leaving a fan in a hand-on mode or a hand-off mode. The system is now required to monitor itself and to provide notification if the system is not running properly. It also has minimum specs on the sensors themselves, and truthfully, it's not overly stringent. It's pretty average for the devices that are available today on the industry. So the task force had a strong constituency from the OSHA standpoint, so the health and safety of both the patrons of the garage as well as the employees, workers that might be in the garage for an extended period of time. And the goal is to balance the life safety and energy optimization and system life cycle reliability. So to achieve that balance was the goal and is certainly well within the purview of systems that are available today. The devices themselves, again, the core physics, the core chemistry of the sensors is very mature, widely deployed. Again, there are some devices still on the market of prior generations, but for the most part, the devices that are being installed today are the electrochemical type. But still, there are standards that can be embraced by a manufacturer to get a third-party certification on the performance of the measurement device. And the most well-known standard of those is the UL 2075, specifically developed for gas and vapor detectors and sensors. It specifically is for our application here. And it includes over 40 categories of functional tests under normal and abnormal operating conditions. It requires audits of the manufacturing facility to make sure that it wasn't just the prototype submitted to the lab that works, but that on an ongoing basis, the manufactured devices still meet those requirements. And it has strict labeling guidelines, a UL label with the 2075 standard. So that is one means of ensuring that the device will give you the performance that's expected out of it. Now, one caveat is that the core element, the electrochemical CO element, there's very few suppliers of those in the world. There's a number of people that make the CO sensors for deployment in the garage, but the core element, the component level, is itself UL 2075 approved, but that does not imply that the entire device has been tested and approved to the standard. So again, when we talk codes and standards, the mechanical codes are the minimum functionality. This is one means to validate that the device that you are considering actually is a best case or best practice instrument. So in addition to the International Mechanical Code and the emerging building efficiency standards, Europe is moving even far beyond that. And whether it was the safety of airbags in vehicles, often the Europeans lead the way in some of the safety aspects of devices. The challenge faced in Europe, they ran out of parking spaces 200 years ago, so there's a high preponderance of enclosed parking spaces and also tunnels, which have the same challenges of dealing with the toxic gases as the garages themselves do. So to unify the standards of the various countries in Europe, again, a task force was convened, and it took a while. It took 10 years. But in August of 2014, this new standard, the European norm 50545, went into effect. Now, what this does is it takes the UL 2075 even a step further in terms of hardware and software reliability. The conclusion being that even if you've got an extremely robust instrument that's capable of measuring the gas accurately, repeatedly, and over a long period of time, it all boils down to the control software to make sure that you're achieving what you're trying to achieve. The 50545-1 puts very strict standards on the third-party certifications of the software as well as the hardware, essentially categorizing these now as life safety systems. There is a categorization called SIL, S-I-L, Safety Integration Level, and these are now categorized in Europe as a safety system. And they are closed systems. They cannot be modified with extra devices. They may have communications to the outside world with BACnet or Modbus or other means, but the measurement and control is in a certified environment. And the good news is deployment of systems that meet these standards generally are at the same cost as prior generation devices. Lastly, tying all of this into the Green Parking Council's Green Garage certification, the garage ventilation is one component of that certification. There's a 6-point maximum that can be achieved in this area, and it depends on the type of a control that is implemented on how to achieve the full points. Importantly, one component of achieving those the points on it is not just the presence of a system and a system that is efficient, but that system is being maintained properly. Because again, like the tires in the car, over time they do need to be tuned up. So again, there are stipulations for documenting the maintenance cycle that you've got on your garage ventilation system. And towards this end, the good news is in many jurisdictions, again, be it the California Title 24 Efficiency Code or others, most of this the points that you could achieve with the certification, you've got to be doing those things anyway. As we hear case studies of people that are moving forward with the garage certification, this is certainly not one where it's a consideration of, do I need to spend extra money to comply? The ventilation, as you'll see in the case studies shortly, there is a big economic tailwind. So doing the right thing gets you the points in the garage certification, does provide an extremely safe environment for everybody in the garage, and has a strong economic tailwind. And with that, I will conclude my portion.
Thanks, Mike. Our third presenter today is Frank Nagel. Frank is the founder and principal of Nagel Energy Systems, LLC, a manufacturer and distributor of an innovative demand control ventilation system for commercial garages. He has grown the company from its inception in 2008 as a small regional firm into one that extends its sales and service capabilities to all major U.S. markets. Frank is an active member of the Green Parking Council and the International Parking Institute, serving on the IPI Sustainability Committee and the GPC's Sustainable Technology Committee, for which he helped to craft the association's Green Garage Certification Standard for garage ventilation. In 2011, Frank served as a key member of a California Energy Commission task force appointed to revise California's energy code specific to enclosed parking garage ventilation. The task force recommendations were adopted and incorporated in the California Energy Code, known as Title 24. Frank?
Thank you, Trevor. And thank you, folks, for attending. Obviously, I'm here to talk a little bit about the technology available out there today. And Mike mentioned that it has a good financial tailwind, and hopefully that I'll be able to convey that by the time I'm done. I'd like to provide a little context to the technology available today, and in doing so, I'm going to be a little repetitive and from the standpoint of some of the things Don had to say and Mike had to say. So as we know, that the International Mechanical Code and ASHRAE are the standards for ventilating garages in North America. The Mechanical Code requires continuous ventilation, as Don referenced, during building occupied hours. The exceptions made for when a CO sensor system, demand control ventilation system, is in place. The issue with that now, or a growing issue, is that a number of states, including California, Oregon, Washington, and then certain municipalities as well, for health and safety reasons as well as energy efficiency reasons, they're imposing stricter standards, stricter than the IMC and ASHRAE standards. And in particular, as Mike noted a little bit ago, they're requiring continuous ventilation even when a CO sensor system is in place. I mentioned California, Oregon, and Washington. What we're seeing in the market is that the standards imposed here in California, where I'm calling from, Oregon and Washington, that these standards are being adopted by other states. New York, as an example, where it's being somewhat driven by the utilities in those states, but also the powers that be in those respective states. And the consideration is the same, which is to say balancing energy efficiency requirements along with health and safety standards. So understanding now that the garages must maintain continuous ventilation during building occupied hours, that puts building operators and owners in a bit of a quandary, which is to say you can put up with the added energy costs to meet the new code requirements and just by running your system continuously without a means of controls, a sensor-based means of control in place, or you can pay the stiff penalties for not doing so. So what we see is that oftentimes in commercial garages where the fans are left off during building occupied hours and it's done as a means to save on energy consumption. That's not permissible anymore, and if you're caught doing it, there are stiff penalties to be paid. The nice thing about this is that there has been a quantum leap in garage. The DCV, you'll see DCV technology, that stands for Demand Control Ventilation Technology. Quantum leap in the capabilities to adhere to the strict standards, increase energy efficiency, and minimize energy consumption, and the investment attributes of this technology are compelling, to say the least. So further backdrop, if we're going to lay the baseline here, let's take a look at the energy consumption and the cost impacts of how significant they can be in a commercial garage. Just as a baseline understanding, we've seen garages where 40% of an entire property's energy bill, annual energy bill, is consumed by the garage ventilation system for a commercial property. Ocean View Village is right here. It's in San Francisco, 450-car garage, consuming roughly $400,000 a year. They had no sensor system or controls, means of controls in the garage. And that's a large mixed-use facility in the Excelsior district of San Francisco. So they're paying $62,200 plus a year, or $5,200 a month, to ventilate the garage. And that represented, and this is according to PG&E's inspecting engineers, Pacific Gas and Electric, greater than 30% of the total annual cost, energy cost for the entire property. Pacific Renaissance Plaza in Oakland, it's a large garage, 900-car garage. That's a 300,000 square foot garage, ventilated by a total combined 370 horsepower of motor. Now, in this case, this is where, to go back to Mike's comments, this is where there was a control system in place, CO sensor systems tied directly back to the motor, an on-off sensor system, and those sensors had failed. And they had been failing for a while, and the fault signals, whenever a sensor would issue a fault signal, would send that signal back to the motor, and in turn, 375 horsepower of motor would cycle on. So the result was that they were consuming, even though they had a CO sensor system in place, albeit one that was failing, they were consuming 254,000 kilowatt hours a year, and peak demand at 295 peak kW a year. Now, in the PG&E territory, peak kW consumption can be 60 cents or higher per kilowatt hour. So you see the cost, $52,000 or $4,350 per month. The Gateway in San Francisco, large garage as well, 420,400 kilowatt hours a year consumed at a cost of $58,000 plus, and $4,800 plus per month. In that case, the garage fans run 24/7. 600 California Street. Here's an example of a garage where they actually turned off their motors. They would run their motors for an hour in the morning, an hour at lunch, and an hour in the afternoon. It was 130 horsepower of motor. And they did so as a means to control their energy costs. What they didn't recognize was that when they were turning their fans on at lunchtime and in the afternoon, they were running them in the midst of peak demand. There's also running 130 horsepower worth of motors, so they were still consuming in excess of 241,000 kilowatt hours a year. You'll see this on in a few slides in terms of what the solution was for this particular property. And last but not least, Park Point Apartments down in Burbank, California, 327,000 kilowatt hours. That represented, there's a typo there. It says nearly 39% of the total annual energy for the bill. Actually, our numbers show that it was in excess of 40%, just slightly in excess of 40% of the total annual energy bill at a cost of $48,000 a year. So hopefully these examples demonstrate just how costly it can be to ventilate a garage. So then let me provide some context in terms of new technology by taking a look at the Incumbent Technology. That's an on-off DCV system where the sensors serve as the primary means of controlling ventilation in the garage, where you have a sensor spaced roughly, according to old code, 7,500 to 10,000 feet apart in the garage. They send a signal to turn the garage fans on when a CO trip point is met. In the Bay Area, it's now 25 parts per million, but in the Bay Area, in a lot of communities, it was 35 parts per million. So when the CO levels hit that level, the signal is sent to the motor to turn on, flush out the garage. When CO levels drop below the set point, the motors turn off. Now, utilities give that type of system credit for saving upwards of 90% on kWh consumption. Trevor mentioned that I served on the task force for the California Energy Commission. We conducted an audit and in going around and auditing various garages and taking measurements, checking systems, and what we found was that 90% of the garages in California are on-off sensor systems. They possess a 90% failure rate due in part to the design flaws that Mike referenced, as well as maintenance, which are tied to the design flaws, meaning that a lot of these older sensor systems fail off. That is to say, when the sensor fails, it does not send a signal back to the motor to turn on and let a chief engineer or a building maintenance person know something's wrong. That was a big concern for Cal OSHA in terms of health and safety concerns, knowing that these motors are not working in conjunction with the sensors, and there could be any type of gas from CO to radon to what have you ventilating throughout the garage. It also ignores the impact of the stack effect. If any of you have tried walking into, and I'm sure you have, walking into an office building at any downtown, LA, San Francisco, Boston, where have you, and you pull on the front door and there's kind of a suction effect. Well, that's typically the result of the garage fans being off in the basement, and in turn, the HVAC system that serves the upper portion of the garage, putting that HVAC system in the position of having to ventilate not only the upper portion, but now it is ventilating the lower portion of the property, the garage, sucking up whatever it can through ventilation shafts, elevator shafts, etc. And that effectively seals off the building and creates that stack effect that I just referred to. And that results in health and safety risks because whatever's in the garage in terms of CO, radon, NO2, what have you, is now being sucked up into the main portions of the building. Other issues with the on-off systems are that it typically switches on when energy costs are highest. From noon, in California, from noon to 6 p.m. is peak demand periods. So whenever people are leaving office buildings and there's a line of traffic looking to get out, if those fans turn on for 15 minutes or more, you're going to get hit with peak demand charges. The other thing is it hard starts motors, which is a huge energy expense, and puts a good deal of wear and tear on the motors. So now let's talk about variable flow systems. It's a sensor-based variable flow system designs in or syncs variable frequency drive technology with a control strategy that first enables the motors to run continuously at low speeds when CO levels are de minimis, and in turn meet the code requirements, the recently adopted code requirements of 0.15 CFM per square foot on up to the maximum ventilation rate of 0.75. In doing so, it creates a reservoir of fresh air such that CO concentrations are prevented from really exceeding that predefined trip point, whether in, let's just use 25 parts per million. It prevents CO levels from getting up there for an extended period of time. And in doing so, it minimizes the number of times your motors must ramp up to flush out the garage. It also, give me 1 second, it also incrementally increases the motor speeds. This is where the VFDs come in a control strategy, deploying a controller. As Mike mentioned, there now needs to be a controller between the sensors and the motors. And depending on the sequencing and how you deploy your VFDs, in our case, our system will incrementally increase the fan motor speed in the ventilation rate in context to CO levels, meaning that if CO levels go to 26 parts per million, the system will ramp the motors incrementally to meet 26 parts per million and push seal levels back down below the threshold of 25 parts per million. And it does so almost instantaneously, and that's a result of having already created the reservoir of fresh air. What we see through 6 years of trending is that the motors, when they ramp, the ramp period before they push seal levels down are between 2 and 4 minutes, which means that you're never or practically never going to be hit with peak demand charges as a result. And you can see here an overlay of what a variable flow demand control ventilation system would look like. And the systems today, including ours, are internet-based, meaning you can manage it remotely. Lou Cuneo can talk to that a little bit. Okay, so now that we know what technology is available, and let's take a look at a few cases where they've been deployed. You can have your cake and eat it too. The Ocean View Village, a variable flow system was installed there, run on a 24/7 basis, achieved a 95.4% annual savings. And by the way, every one of these projects that I'm going to review have been reviewed by inspecting engineers for the regional utility. And in each instance, on the post-installation side, the motors have been data logged for an extensive period, weeks, on 1 minute intervals or at 1 minute intervals to verify the savings. So in this case, 95.4% in excess of 381,000 kilowatt hours from the baseline of 400,000. Peak demand reduced by 95.5. Post-ventilation, post-retrofit cost to ventilate the garage reduced to just $2,782 a year, a 95.5% savings. That's down from $62,000. In this instance, PG&E engineers recognize that the retrofit reduced the cost for the entire property by 30%. We like to crunch numbers too in order to Mike's point about the financial tailwind or the investment tailwind. In this case, the project, based on the cost of the project to install and the amount of savings that it recoups, this project had on a roughly a $59,000 installation cost, a $672,000 net of investment, net present value. Paid for itself in 12 months, not including the utility rebate. And as you can see, the rebates here are pretty good in Northern California. From a greenhouse gas equivalency, well, the numbers speak for themselves there. Passenger cars, the equivalent of 53 passenger cars, the miles driven. Again, the numbers speak for themselves. Park Point Apartments, which I referenced earlier, annual consumption there reduced by 94.2% after a variable flow system was installed. Peak demand cut by 94.2%. Energy bill goes from $48,000 to $2,700, also a 94.2% savings. And this is where we cut the entire property bill, as verified by Burbank Water and Power, by 40%. Net present value on a $69,700 installation cost exceeds $490,000. Paid for itself in 18 months, not including the rebate. And again, you can see the greenhouse gas equivalency savings. Significant to say the least. And with that, I'll be quiet and pass it back to Trevor to introduce Lou.
Thanks, Frank. Our final presenter, Lou Cuneo, is going to share his experience with deploying an energy-efficient ventilation system. Lou has been the Director of Facilities Management at the American Academy of Ophthalmology for 5 years. In that time, he has had the opportunity to bring energy management improvements to the Academy's headquarters, a 43-year-old building in the heart of San Francisco's historic Fisherman's Wharf. Lou began a public safety career at age 18 as a firefighter in Atlanta, Georgia. Training and education opportunities allowed him to serve not only as a firefighter, but a medtech, bomb technician, law enforcement officer, and arson investigator before becoming the department's chief of training. He retired from the Atlanta Fire Department as deputy fire chief in charge of Atlanta's International Airport. Appointed Georgia's Deputy State Fire Marshal for 3 years, Lou was responsible for statewide fire prevention, fire engineering and inspection, as well as fire and arson investigations. Since leaving public safety, Lou has held management positions in the private sector's safety, security, and facilities disciplines. Lou holds a Bachelor's of Science degree from Brunel University and a Master's of Public Administration from the University of San Francisco. Lou? Lou, is your line on mute? We're having trouble hearing you.
Oh, my apologies, Trevor. I thought you had that under control. I noticed that by a few phone numbers that we have some people from the Atlanta area, so hello to my former colleagues there. Here in San Francisco, you see a building there that is at the corner of a very iconic area at Beach and Hyde Street on Fisherman's Wharf. If I was able to turn that picture around, you'd see a picture of the cable car turnaround and the Golden Gate Bridge. I think Frank did a very eloquent job of describing the numbers and the argument that you can make for undertaking a project like this. But from my standpoint, I'm just a facilities guy. And the issue of my garage ventilation is no more important than a lot of other facility-related aspects. However, we were in a position to introduce this technology very quickly. I have a 130-car garage. I call it a boutique garage. We serve not only our employees here at the Academy. We have about 200 employees that serve 32,000 ophthalmologists throughout the world. And about a third of those people park in our garage Monday through Friday. But we also serve what we refer to as transients, which means people that are visiting Fisherman's Wharf. We have a couple of very nice hotels in the neighborhood that use the garage. And all of that to say that it's a very busy garage from time to time. The 130 spaces actually can hold about 160 cars because we do have the valets. And the valets are working in the lower levels. We have 2 subterranean levels of the garage. And their comfort and safety is paramount to me. So when we were able to introduce this technology, it did a couple of things very, very well and very, very quickly. One of them, I can say my elevator speech when somebody asked me not too long after we implemented this a few years ago, if the CEO said, hey, how's that garage ventilation going? I let him know very quickly. I appreciated the investment. We were able to take our investment in the utilities for the garage from about $20,000 a year to $1,200 a year. I said that part very slowly so he understood the significance. Also let him know that the fans that were blowing people's hairdo as they walked by the vents wasn't happening anymore. In fact, a few people complained that the garage fans were not operating any longer. But in fact, they were actually operating at a really steady 25%. And as necessary, when the sensors detected the 25 parts per million of CO2, they would ramp up slowly, they would clear the garage, and then they would ramp themselves back down. So very efficient. From an interface standpoint, I can look, in fact, I can turn around right now in my office and look up at the software interface that lets me know which of the sensors are reading how many parts per million. It's a lot of fun when people walk into the office and they ask, what is that? And I can explain to them, and they always walk out going, hey, that's pretty cool. But again, you know, this is a small portion of a facility director's life, but it was also cool receiving a $15,000 check from PG&E as a rebate for the project, and the project paid for itself in under 18 months. So again, part of my elevator speech to the CFO who I work for and our CEO. The information on this page, just reviews the expenses, the net present value calculations. A lot of this stuff is necessary, but it really doesn't tell the story in the way that my colleagues and the users of the garage want to hear. They want to know that it's safe. They want to know that it's clean. and they also want to know, well, what else are you doing? So as a result of that, we've also done LED lighting throughout the garage. We have 6 electrical vehicle charging stations, all of that to tell the story that we're very interested in making this part of our operation as green as possible. So with that, Trevor, I'm going to turn it back over to you, and if anybody has any questions, I could entertain those, but also anybody who's listening, if you're ever in San Francisco, please look me up. Take care.
Thanks, Lou. So we'll open it up to questions. First question I have for you guys is, what's the main driver for folks that are deploying this types of technology? Is it making these installations to meet code, or is it really these great economic benefits that you're seeing?
Lou here. I'll take a shot at that question. For me, code compliance as a former government official is very important to me. But the real issues are around, as a not-for-profit organization, the Foundation for the American Academy of Ophthalmology owns this building, and on behalf of our 32,000 members, want to make sure that we're operating it as efficiently as possible. So as a result of that, anything we can do to lower our operating expenses, we're going to try to do that. But larger than that is doing the right thing. And as you can imagine, here in San Francisco, California, as with a lot of major cities throughout the country, we're trying to drive environmental awareness and just, again, doing the right thing. Thanks, Lou.
Mike or Frank or Don, do you have anything to add to that?
Do me a favor, repeat the question.
What's the biggest driver for folks that are deploying these systems? Is it code reliance, doing the right thing, as Lou said, the economic benefits?
My experience in out there in the trenches is that when people see, A, how much they're spending just to simply ventilate their garage, and B, see what the savings opportunity is, both from an energy consumption and cost savings, that's a big driver for them. When you break down the numbers, you can see that it's a smart investment. So I would say the cost, the utility cost to ventilate the garage is a big driver, and the desire to get that cost down.
Thanks, Frank.
And this is Mike. I'll basically echo the same thing. Again, the economics are such a tremendous tailwind. So again, it's being a good community citizen and doing the sustainable things that you can do. But to use an overused expression, this is kind of the low-hanging fruit, because in addition to achieving such tremendous energy savings, the economics are just are there. So what we see, as Frank said, in the trenches is, for many years there have been a number of ways to try to accomplish this. So really, how do you go from here to there? It begins with the baseline of what do you have in your building. Sometimes there's constraints on the existing fans. There's other constraints that you might have. But regardless of whether you've got any sensor system now or there's none, again, it's fairly simple to do a baselining on what you have and then map how to get the most effective system from there. Certainly replacing the fans in a building would be a lot more expensive than what we're talking about, but most of this is bolt-on. Again, there's an investment cost. We're going to add in variable speed drives on the existing fans, and again, the economics just make all of that worthwhile.
Yeah, this is Frank again. The traditional on-off sensor system is, to be blunt, it's far less expensive. You have a sensor that has to tie back to a motor, and the sensor serves as a means of control, versus, as Mike referenced, to the fact that you're involving a controller now, variable frequency drives, etc. It's certainly a bit more to bite off financially, but what I've certainly found is that by showing the investment attributes of the variable flow system, it kind of softens the blow, financially speaking, when they see, for instance, the net present value and the cash inflow generated from a system like this.
Okay, our next question is, are there other types of sensors available today aside from the electrochemical and solid state?
This is Mike. I'll take a shot at that one. So when I was talking earlier, I had mentioned that there was previous generation, and oftentimes the solid state is the one that comes up in that regard. It is a completely different physics of measuring the presence of the carbon monoxide. It's got many disadvantages in that it has high what's called cross-gas sensitivity. So the electrochemical is much more selective to the carbon monoxide. The solid-state sensors get a lot of false positives and therefore will ask for more ventilation than is truly reflective of the carbon monoxide. Plus, the solid-state elements themselves are a heated element, so they themselves consume electricity 24/7. It's like those little pirate devices you have in your house that are just eating energy whether they're helping you or not. So solid state really is fading away, and electrochemical is the dominant technology now. There is also the ability to sense the carbon monoxide with infrared technology, dual beam infrared technology. That is utilized now for carbon dioxide quite commonly. Carbon dioxide is actually a more difficult gas to measure. So although the infrared can be deployed for carbon monoxide, it's not necessary, so it's really hard to justify the incremental cost. Now, one benefit of the infrared technology is much longer stability, less change over time, but the first cost on it tends to be much, much higher, and again, generally it is not economically a good choice to make. The electrochemical really is the dominant technology today.
Thanks, Mike. Our next question is your experience as installers that variable control technology results in a decrease in the amount of horsepower that a facility system will need?
This is Frank. I'll take that one on. I'm going to go back to mechanical code requirements, and Don touched on this earlier. So prior to 1999, the mechanical code required 1.5 CFM per square foot for a ventilation rate in the garage. Thanks to catalytic converter technology in cars, in 1999, they cut that in half because cars were not emitting as much CO. From a practical standpoint, that means that any building designed and built in the mechanical system designed and built within that substructure garage, let's just assume it's a below-grade garage in an office building, as an example, that was sized to meet 1.5 CFM. So if you have, depending on square footage, say 220 horsepower motors, that was designed to meet a ventilation rate accordingly. What it allows you to do with a variable flow system is you don't necessarily have to change your motors out and reduce your horsepower accordingly to reduce the ventilation rate. The variable flow system does that for you, meaning that you can play within the minimum ventilation rate of 0.15 and now go up to a maximum ventilation rate with your system of 50% of motor speed. That will meet the 0.75. In other words, your motors with a variable flow system will never exceed 50% motor speed. The only time that would change is if you're tied into a fire life safety system, and then you can program the VFDs to be overridden and go to 100% speed in the case of fire. And we do that quite a lot, actually. So the primary point is you don't have to necessarily reduce the horsepower of the motor. The VFD really takes care of that for you.
Thanks, Frank. Our next question goes into geography a little bit. So would facilities in the Northeast and other parts of the country realize similar savings to the projects on the West Coast that we went over in the presentation?
Frank again. Heck yeah. The motor consumed by the energy consumed by a motor in Worcester, Massachusetts is going to be the same energy consumed by a motor in Burbank, California. If it goes more toward weather considerations, etc., in your ventilation rate, I could ask Lou to jump in and talk about how he manages his system, particularly in the summer. Lou, you there?
Yeah, we benefit from a very moderate, almost Mediterranean climate here. So the temperature right now is 60 degrees, and it never varies more than 10 degrees here in our area. So we're as much savings as we've been able to achieve with such a moderate type of climate. I can only imagine that the more severe or extreme temperature changes would benefit from that even more.
And this is Mike. Let me add another comment on that too. So, all the examples that Frank and Lou were talking about today were extremely hard data on the energy savings. Now, some of the intangibles, some of the softer data. Imagine if you're over-ventilating your garage. That is, you're operating your exhaust fans and throwing out air. Well, that air has to be replaced. So to Lou's point, where we've got a very consistent climate here on the West Coast, if you've got a particularly cold climate, a particularly humid climate, if you're over-ventilating, you're actually drawing in that less comfortable air. So the experience of the visitors in the garage, they are going to be experiencing that outside air to a much greater degree. So that's another soft benefit, as well as Frank was saying, just the noise level when you're running these fans either at an excessive speed or when you're turning them on and off and hearing that extremely disruptive sound of the fans coming on and off. By providing a variable flow system, running the fan very slowly and not sucking in any excess outside air, you're basically creating a much more pleasant environment in the garage as well.
Yeah, and Lou, back again, I can echo his comments because the valets that work in our garage, they're spending many hours at a time down there, and the difference in the noise was dramatic, and that's why they kept reporting that the fans weren't working when in fact they were.
That's all the time we have for questions. I'd like to thank our 4 presenters for today for sharing all this great information on ventilation systems and the opportunities for improvements in terms of efficiency. As of tomorrow, we'll have the presentation recording as well as the slide deck available on the Green Parking Council website at the link here, as well as our panelists' contact information. So if you have any additional questions, I encourage you to reach out to those presenters. Additionally, if you have suggestions for future webinars, please email me at trevor@greenparkingcouncil.org. Thanks for joining us today.